Am I audible now, guys? Thanks for hanging in there, first of all. Thank God. Okay, so welcome you all to the 11th week of live interaction session for the course Principles of Downstream Techniques in Bioprocess. Let me share my screen. Do let me know if it's visible. Okay, so I haven't loaded my PPT. Yeah, so this is visible, right? Okay. Okay, so I've enabled chat on my phone so I can see you guys answer. Let's get into the topics for the week. So this week we are continuing to deal with chromatography and a little bit of crystallization. So first question for the day is: a protein is eluted from a 200-liter packed column which has a void fraction of 0.25. Calculate the elution volume if the equilibrium constant is 10. So this week we have just 7 questions, all simple ones. So take your time. I hope you went through the lectures and are familiar with the formulae. A protein is eluted from a 200-liter packed column. Has a void fraction of 0.25. Calculate elution volume. Remember this formula. So can you now substitute everything into this and tell me what the answer is? So you know what epsilon is, you know what K is, and we have V given. And elution volume is given by Q into T naught, right? So if I just bring this from the denominator all the way to the numerator on the left side, Q T naught is equal to epsilon plus 1 minus epsilon into K into V, which is 0.25 plus 1 minus 0.25 into 10 into 200. Any answers? That will be 7.5, 7.75, right? So I'm getting 1550. Guys, am I still audible? Are you all listening to me? And I hope you are parallelly calculating or solving the sums. Okay, let's check the answer. We got 1550. I hope I believe it should be in. We don't know the units of this particular problem, because except for liters here, we don't have units mentioned else anywhere else, and we don't know what for equilibrium constant either. Clear? Any questions? We'll go to question 2. If the percentage of maximum concentration with respect to the concentration injected is 3.5%, how many theoretical plates the column has? Right? So when you have, if I'm inaudible, please let me know, because I have no way of knowing unless you tell me through chat or just unmute yourself and tell me. Okay. I hope the color is visible. So this is the T naught, the time at which the peak elutes, or it can also be in terms of volume if you are measuring the volume. So the maximum concentration of the peak is given by C naught. So if the percentage of the maximum concentration, which is C naught, with respect to the concentration injected. So you have a chromatographic column, either horizontal or you can look at it vertically, and you're going to inject some sample into it, correct? So that is CF, which is for F for feed, correct? So into the chromatographic column, when you send it for separation, there is a CF feed, and then it gets purified, separates from a mixture, and then comes out as different peaks, right? So here the concentration of that particular, the maximum concentration in that particular peak is C naught. So the question says if the percentage of maximum concentration with respect to the concentration injected. So C naught by CF, correct, is 3.5, or you can take it as C naught is equal to 3.5 of CF. in percentage. So what would that be? Divided by 100, correct? 0.035 into CF, or C naught by CF is equal to 0.035. You can take it either way, it's the same meaning. Yes. So now the question is, how many theoretical plates does the column have? Right? So last week we had a formula, C naught is equal to CF divided by root of 2 pi n, where n is the number of theoretical plates. So this is what you want. So what should you do? C naught by CF is equal to 1 by root of 2 pi n. And you know C naught by CF is equal to 0.035 is equal to 1 by root of 2 pi n, or 2 pi n is equal to 1 by 0.035 the whole square. Can somebody solve this quickly and tell me? And further, n is equal to 816.3265. I'm just going with 33 divided by 2 pi. So I'm getting 129.9. So I'm going to go with 130 plates. You can also go with 129. There's nothing wrong going with this. Yes, Neha. Do you want to unmute and speak? Any problem? Are you all with me? Can you hear, understand what's going on? No problem, Neha. So let's continue. So are we clear until here? Fine. Welcome, Natarajan. So we are doing the second question on theoretical plates. So if nobody has anything to say, we will move to the next question. So the answer that we got was 129.9. So this is the formula that you will be using for this. Question 3. Increasing particle size increases option A mass transfer coefficient, option B pressure drop, option C resolution, and D void space. Think about it and drop in a text. Is it A, B, C, or D? Increasing particle size in a packed bed chromatographic column. This is one case. Thank you, Sriram. Anybody else? And Sriram, think twice. Exactly. So let's assume these are different columns. Okay, just different scenarios where you have small size particles, bigger, and a little more bigger. Okay, so I've just drawn here in the same column here to show for a given diameter. If this is the dimension of the column, and if you change only the particle size, how the situation varies, right? So see the void volume here, the gaps between the particles here are much less when compared to the gaps that you will get. Although it's not very obvious, but you can imagine, right? You would have played with pebbles or so many things as children and marbles. So even when you try to filter, you will always have bigger particles on top, followed by I'm talking about normal ground filtration of water or something, and then finally you will have silt, which gives even better filtration. As a child, you would have done these science experiments and things. So the pressure when the particles are very tiny, or even during filtration, we saw that the filter medium gets clogged after some time, right? So when the pores are small, the fluid has to be pushed under great pressure. So there's a lot of resistance to the flow. So if you decrease particle size, if the particles are smaller, then the pressure drop would increase. Whereas increasing the particle size is going to decrease pressure drop. Correct? So B can't be your answer. Similarly, you have this formula, right? Sigma square is equal to, what was it? Velocity divided by KLA into length of the column, if my memory is right. Correct? So whenever you increase the particle size, increased particle size means increase in sigma. So if there is an increase in sigma, then there is a decrease in mass transfer coefficient. Yes. So this cannot increase. So A is wrong, B is wrong. Option C, resolution. When does resolution increase? So when you're talking about sigma, base is 4 sigma, right? Assuming a Gaussian model. Uh, so the steeper or the sharper the peak, better is the resolution of a chromatographic column. We have been discussing this for the past few classes, correct? So what does it mean? It has more theoretical plates, or there is more scope for resolving that particular compound within the chromatographic column, which means that you can separate it from other impurities that it is traveling with. Okay, and you also know that sigma square is equal to 1 by n. Sorry, square is there. So let me pick some other color. So you can see here, right? This is separate and that's separate. So sigma square, which is equal to this relation, is also equal to 1 by n. So increase in theoretical plates gives you more resolution. But if sigma square increases with increase in particle size, then n decreases. When n decreases, which means resolution decreases. So C cannot be your solution. So what increases? The void space. When the particle size is large, it will not pack well with other beads. How much ever you pack, you will have bigger spaces than a column with smaller particle size. So the one thing that does increase is void space among the options given here. Clear? Question 4. If the mobile phase velocity is doubled, the retention time from a value of 18 minutes will become what? It's a very simple question. So you know that velocity is equal to distance by time. And here, what is the distance? Chromatographic column is the distance, right? So the fluid is flowing at certain velocity, correct? And you have a length L. So T, retention time T naught is equal to V by L by V, correct? I'm just taking time there and velocity here. So you have T1 is equal to L by, there's no change of the length of the column. Yes or no? So only we are just talking about velocity and time. So we'll just have length as it is by V1, which means L is equal to T1 V1 and T2 is equal to L by V2 or L is equal to T2 V2. Can we equate this now? T1 V1 is equal to T2 V2 and V2 is twice V1, correct? So you can cancel these out. What is T2? 1 by 2 T1. So it is half of T1 is equal to 1 by 2 into agreeable. I just took the long route here. You just need to know that. I mean, it's obvious, right? When you double the speed, you reduce the time by half. So 18 by 2 is equal to 9. It's that simple. Clear? Shall we move on? The answer that we got was 9 minutes. Okay, question 5. In a packed column chromatography, if the process is controlled by internal diffusion, okay, remember this because we'll be using that particular formula, and the particle size is reduced by half. In order to maintain the same sigma, what should be the velocity when initial velocity is 2 centimeters per second? In case you need the formula, it's here. Sigma square is proportional to, again, if we have the length as constant, sigma square by Vd square of 1 is equal to sigma square by Vd square of 2. Particle size is reduced by half in second case, and you are maintaining the sigma also same, correct? So Vd square 2 is equal to Vd square of 1, and you know that in second case it is half. So V into half of d1 the whole square is equal to v1 into d1 square. So that will be v2 into d1 square into 1 by 4 is equal to v1 into d1 square. And you know that velocity 1 is 2 centimeter per second, but before that let's just cancel this out, and let's substitute v2 is equal to 4 into v1 is equal to 4 into 2 centimeters per second is equal to 8 centimeters per second. Was this clear? Do you want me to repeat? So the point here is you want to maintain the sigma as same, and we are not changing the length of the column. We are just uh, varying the velocity as well as actually only the particle size is modified, and we want to know how it will affect the velocity. Correct? So keeping sigma square L as constant, Vd square of first case is equal to Vd square of second case. So you're reducing this by half, so there's a denominator of 4 which goes to the other side, and these get cancelled. So V2 is equal to 4 times V1 is equal to 8. Clear? You guys are being extremely silent today. Alright. Question 6. A crystallization process follows McCabe law with a growth rate of 0.04 millimeters per minute, not in hours. If its dimension is 1.2 millimeters, how long will it take to reach a dimension of 2 millimeters? So let's take a minute there. So what's McCabe's law? Growth is equal to, question is how long. So you want to find this delta T is equal to delta L by G, and they have told you that the growth rate is 0.04 millimeters per minute. Okay, and the length is 2 millimeters minus 1.2 millimeters divided by 0.04 millimeters per minute. So what would this be? Does anybody want to calculate and tell me? Thank you, Natarajan. So it takes 20 minutes for the crystals to grow from 1.2 millimeters to 2 millimeters. So we had our question in minutes instead of hours. So our answer will also be in minutes. Question 7 and last for the day. Latent heat of vaporization of water is 40.8 kilojoules per mole. I put in a heat of 2500 kilojoules of heat at its boiling point. So how many kg of water will evaporate at this temperature? Neglect all losses. So using this, what can I do? Heat of vaporization of water is 40.8 kilojoules per mole and the input heat is 2500 kilojoules. So with this two information, what can I do? I can find out how many moles of water I can heat. Yes. So if I divide 2500 kilojoules by 40.8 kilojoules, I can find out how many moles of water I can first evaporate, right? So let's do that first. So 2500 kilojoules by 40.8 kilojoules per mole. So that gives me 61.275 moles of water. And water is 18 gram per mole. Right? 1 mole of water is 18 grams. So if I multiply this with this, what can I get? I can convert water in terms of grams, right? So 61.275 moles into 18 gram per mole is equal to 18 into 61.27, getting 1102.95 grams. What is the question? How many kgs of water? So that will be 1.103. I'm going to go with 3 kg of water. Or let's say evaporate. Clear? So my answer is 1.103, which falls within the range, so I'm happy with it. So that ends my set of questions for the week. Do you guys have anything to share or ask? Or if you want me to redo any question out of these seven, you can tell me. That's it. Okay. So if nothing's there, thank you all for joining. Please do uh, show up next week. I think that'll be the last class for this course. So looking forward to meeting you all there. And hope these sessions are useful to you. If you want me to discuss something, you can tell me. If you want me to take some particular problem in the next class or so. Otherwise, let's just close this session. Happy weekend.